Thank you, everybody, for joining. This is now our 18th meeting. We're almost up to 20. Maybe we will have finished by 20. We can hope. So the agenda for today, we're going to be talking about a new proposal, primarily around grid meter and EE weather. We're also going to do a recap of our last meeting. We're going to talk about some population results, some model changes that we've made as a result of these population results, and our next steps. So to start this this proposal off, where we're at currently is the daily model is done. We have a better version, and that was released in OpenEEmeter 4.0. We're now 60–70% of the way done with the hourly model, and hopefully within a working group session or two, that will be fully released as well. Now, these two things are used primarily for savings measurements, but savings measurements using these models lack information about a lot of additional external variables, state of the economy, if COVID is happening, any number of things really. And so this is where the use of comparison groups is highly advised. Now, GridMeter is a library which its entire purpose is to generate comparison groups. And it originates from another working group outside of the Linux Foundation Energy. So what we are proposing is for Recurve to donate GridMeter to OpenEEmeter. Point 3 here. This is for all of the reasons I just mentioned before, in that GridMeter is used. These comparison groups correct model predictions using population trends and external factors, and then that will make all savings measurements far more. We're also proposing, jumping back to 1, of renaming OpenEEmeter. We don't yet have a name for it, but the reason why we're talking about changing the name is because if we do this, then instead of having to type in from eemeter.eemeter import blank, which is kind of doesn't make a whole lot of sense, but it's the structure of the library as it currently stands. Instead, it could be placeholder.eemeter, and instead this placeholder name would act as an umbrella for the entire everything underneath it, which means that we could add in like EEmeter would now be a submodule within this library. GridMeter would also be a submodule, and we could also make EE weather another submodule. In essence, this gives us a lot more flexibility for the future in order to add additional features to our library without making it so that the library itself is focused only around AMI meter-based savings. Now, why would we want to move EE weather to under this umbrella? Well, everything that I just mentioned, GridMeter and OpenEEmeter, is reliant on EE weather. And there's also quite a few places where having a more natural coupling between EE weather and like the data classes for the daily and the hourly data classes would make things quite a bit easier. So with all that said, what are people's thoughts on this?
I mean, I guess on the one hand, it's a pretty common model to have the, total package and the source code both be named the same thing. But if we wrap it all together, then it definitely makes sense to have some other name as the umbrella. And I guess this is becoming a more popular model for code repositories to do the mono repo and have everything sort of synced in versioning so that you can have it all, know that it's all compatible versus needing to pin the dependencies and make sure that you're not getting ahead or behind with things that work together like EE weather and EE meter. So seems like it's more or less going in the right direction, but I'm not the expert on that kind of software engineering. So open to other people's thoughts as well.
I would add to that, Ethan, that brings to mind another reason why we're wanting to do this. So for GridMeter, there are quite a few common functions that exist in GridMeter and OpenEEmeter. Right now, we have to maintain both of them if we make any changes to those functions, and it's cumbersome, to say the least. So putting this all together means that we could also move those common functions out to its own folder, and then we can just reference those common functions throughout the rest of the library.
So I don't know how much visibility you have into the user base, but I think that if you use EE meter, you're very likely to be using EE weather at the same time. If you're using grid meter, you're probably going to be using EE meter. It's possible that someone would use EE weather without the other two. Have you heard of anyone doing that? Or do you have any sense from the stats of whether that might be happening?
I have heard of this concern before, and to me, that is more reason to have the placeholder name be somewhat generic, because then somebody's not going to feel so strange about wanting to use EE weather, which is a submodule of something else. To me, it's kind of like somebody wanting to use sklearn, but they're only interested in the regressors modules. It's a common thing.
Yeah, I mean, to some degree, like it's not probably the top concern of this working group to support someone who only wants to use EE weather to have a Python API to know a weather data or something like that's. I mean, that might be useful for someone, but it's not really like what gets us up in the morning. So I'm not. I don't want to spend too much time thinking about it.
Okay. So if there's no other concerns, then we'll look further into making this a reality, and then we can kind of see what everybody thinks when it's already in there, and hopefully it'll be a positive thing, as it will only require downloading a single library and installing it, as opposed to the 3 that currently exist if you use all 3. Okay.
What's it going to do in terms of like history and code? I don't know. I mean, you're basically going to start a brand new project and then just drop this in there as version 1, right?
No. So currently we have a branch inside of OpenEEmeter where we have moved GridMeter over, and we have also moved the entire Git history from GridMeter into EEmeter through that branch.
Oh, great.
We're going to probably do the same thing with EE weather, though to be quite honest with you, that right now is at the bottom of our priority list because everything functions fine without that. The bigger priority here is get GridMeter in, get the hourly model in, and then possibly rename the entire package. Now that we have GridMeter and OpenEEmeter in there, I think that is the time to rename the top level umbrella package, I guess.
Okay, that's good news.
All right. So with that, let's do a recap of the last session. So again, we have looked at a lot of different models for the hourly model. And for the current one, we are about 11 times faster than Caltrack 2.0. However, this is without interpolation. This number will need some modification now that we are doing interpolation. The new model has 2, but 2 is actually encompassing in number of additional columns, one of these being GHI or solar irradiance, and supplemental data being more of a research-based addition that you can add into any model. And we are also in a state where interpolation is not a nice to have, it is an absolute necessity. because the way that the new model works is that we actually predict 24 hours at a time, whereas the OpenEEmeter 3.0 or Caltrack 2.0 output, and it's the way that it works is by doing each individual hour. So this means that every day has to have complete features, or we have to exclude that day, which means we need to be able to interpolate NAN values in the features. And when I say features here, I'm referring to temperature observed, basically just those two. Right now, we are of the opinion that there is no way for us to interpolate supplemental data because we don't know what that supplemental data means. It's also more of a research function, so it's less of a concern. GHI is also likely to need to be interpolated, but it's also more likely that GHI, when I say GHI, that's referring to solar irradiance, that is more likely to be a complete data set right out of the box, just because of the way that you normally get GHI. So we're mostly focusing here on temperature and observed. Now, there are different types of interpolation. You can do univariate or multivariate. You can change the function on how it and how it reads the data. So that could be a linear interpolation, cubic, nearest data, so forth. And previously, what we talked about last time was using a multivariate radial basis function interpolator. This function has actually lost the race, and I'm only going through it just so that to remind everybody where we were at. Now, the way that this one was working is we would look at the week prior, the day before, the day of, the day after, and the week after in order to get enough data about how does this feature generally work. Is there a weekly component to it? Is it a daily cyclical, that kind of thing? And that's the information we were trying to draw from that. And then we would fit based on the available data points for each day and interpolate for the NANs. The reason why this one was rejected is because it ended up being an order of magnitude slower to complete the interpolation. However, the actual value in the error that we were getting from the multivariate RBF wasn't really a whole lot better than the next method that I'll be talking about here very shortly. So with that, let's go into, or actually, before I move on, are there any questions about the last session or anything that I've discussed so far? All right, moving on. So let's talk about what we've been working on since the last meeting. And we have looked at changing our interpolation to an autocorrelation interpolation. So what does this mean? Well, first of all, what is autocorrelation? Imagine that you have this signal F shown as in this blue line. Now, if you do an autocorrelation, what you're doing is you are basically passing or crossing over this signal and multiplying it by itself. So that's what this is representing here, is the signal being crossed over with itself and then being multiplied. And since you're multiplying them together, when that signal rises, then and both of them rise at the same time, then the multiplication of that becomes quite high. But if they cancel out at all, then it will be lower and lower, which means that the purpose of an autocorrelation is to tell you at which lags is your signal behaving similarly to what it was at another time. The way that we're using this is that we find the n largest peaks, and this gives us our index, lag, and lead. So then, whenever we have a NAN, what we do is we average those lags and the leads for each of the NANs. And this gives us a new value that we can interpolate by. This is also very useful because it automatically picks out how the signal is behaving similar to itself, and how whatever, even if the signal is cyclical at 36 hours, we'll still see that. And we will still use that when we're averaging. So this is very, very flexible. Now, this does not always work, because sometimes whenever you're doing those in lags and leads, you might be missing all of the data that would work for that. In that case, we defer to a time-based linear interpolation. If that fails, then we use either a backwards fill or a forwards fill. These are not likely to ever be hit. Most often we get 90-95% of the NANDs using the autocorrelation, and then the linear interpolation takes care of the rest. Any questions?
Travis, I want to add one thing right here. So for the autocorrelation, when we do it once, so imagine we have a bunch of NANDs in a time series, and those we wanted to interpolate those NANDs. And then one time we go through all of the time series, we replace those ones that we can, and then we look at the time series one more time, which is like those NANDs now they have values. So if there's any more NANDs, then now we can use those lags that we just replaced. And we do that all the time, so we can have all of the NANDs as much as possible filled. If it doesn't fill, I mean, when we go to the next round of looking at the whole time series, if actually nothing changed, then we go to the time-based linear interpolation.
But what, I don't know if I quite follow. So why wouldn't all the NANDs be filled on the first pass?
So imagine a number of lags is 5, okay? And for one single time step, you have multiple NANDs around it for those lead and lags. So that NAND value basically doesn't have any helpers to take the mean value. And if we don't have it, and the next time, hopefully, one of those, like couple of those NANDs will be replaced with the other highly correlated NANDs in their timestamp, and then we do it again.
So the autocorrelation is finding a single lag term to use for filling, not multiples like we were doing before.
It's multiple. So so imagine we have right now focusing on temperature. We choose the lag from minus, I don't know, minus a week to plus a week, and then we roll these time series alongside with each other. And then for each lead and lag, we have one number. We have one autocorrelation, basically, one correlation, basically. And we rank them, and based on the highest correlation, we choose n of them. Right now, n is, Travis, I think it's 10.
For temperature, it's 6.
For temperature, it's 6, and for observed, it's different. So basically, multiple helpers, lags and leads.
Okay. Thanks.
Mm-hmm.
I have one question, Travis. So is this about the temperature or the energy consumption? So for example, if the NAND exists in the energy consumption, what is the process to fill them?
Same. We use a different number for n, though.
Okay, so I have a hard time understanding this autocorrelation. From the conceptual perspective, autocorrelation is not a good thing for the energy. For the temperature, I can live with that. Like for example, with the interpolation or kind of some backward filling or forward filling, there is no issue there. When we are going to fill the energy consumption with that autocorrelations, my understanding is we are plugging in the temperature or weather as the independent variable to find the regressions for the energy consumption. When we are doing the autocorrelations to fill those missing value for the energy consumption, we are removing the impact of the independent variables to the energy consumption. Having said that, if you are going to consider the bias for the energy consumption, or some like a parameter increase the consumption or decrease the consumption, all of them are going to be considered as independent variables. By having these autocorrelations, we are removing the impact of those parameters, which is not a good thing. So yeah, what do you think?
I can answer to that. So for the observed values, we have baseline and reporting year, for example. And we do that autocorrelation based on each section by itself. So they're not basically talking to each other. And let's focus on the baseline right now. When we do this autocorrelation, that basically means each timestamp observed value has some sort of correlation with the previous or the lag or lead observed value in different timestamps. So basically it means there is a cyclic correlation. Either it's 24 hours, 1 hour, 2 hours. So they're correlated. And we're just using them to just have a guess for that specific timestamp. And that's solely based on the signal by itself. So we're not looking at the temperature to have a guess for the observed. We're looking at the observed value by itself.
Yeah, this is the definition of the autocorrelation. So the autocorrelation in a simple language means each energy consumption depends on the prior time frame or the forward time frame. So we are linking the energy consumption to the time of the use. This is the definition of the autocorrelation. What I'm saying that for the energy, we are introducing the independent variable to remove the impact of the time of the consumption to our prediction. So autocorrelation is not a good thing for our predictions. We wanted to have some independent variables, such as GHI or temperature, to predict the consumption, which is not necessarily depends on the time of the use. For the Caltrack or time of the week and temperature, the approach is completely different. We are interpreting the occupancy rate based on the time. So from the, let's say, the weekend, weekdays, or a specific time of the week, we are reflecting the occupancy by having that time of the week and temperature. So that's, I would like to kind of segregate that time of the week from this, this conversation. What I'm saying that if you wanted to relate or correlate the energy consumption with the time, either from the cyclic one, or this is not a good thing. We wanted to avoid it, but you are introducing that one.
We're basically doing it in the Caltrack in some sort of way when we were talking about our time of the week and even like weekend and weekday. Basically, we're categorized in different point of view. Right now, we're just looking at in a different way the time that is that's highly correlated by itself. So we're not adding any extra.
I respectfully disagree with you. For the time of the week and temperature approach, we are introducing the occupancy. So that is the occupancy, which we are defining it based on the time in each like in each hours of the week. That's a occupancy. So it's different occupancy for each different kind of time. But here is the completely different concept.
So there's a couple things I think to keep in mind here. And then I have a question, Armin, for probably you or Travis. So I'm curious about an aspect of this as well. We are using a cross-validated test train approach here in order to understand the predictive capacity of these models and studying bias, studying RMSE, all those metrics that we know and love. And this interpolation step is happening in the baseline period in order to create complete data sets that we can model using the formulation of the elastic net that Armin and Travis have compiled. So if there's a real issue being introduced, we'll see a degradation of all of those parameters. We'll see potentially increased overfitting. We'll see greater bias, or we'll see worse RMSE. Right now, we're seeing improvements in RMSE. And I don't want to get too far ahead of ourselves here, but Travis and Armin are going to go through some bias considerations as well. If autocorrelation if the fact that there is some degree of autocorrelation that we can pull out of the data in a way that allows us to have a more accurate interpolation, then I don't see an issue taking advantage of that. Autocorrelation might be an issue for models themselves, but in a way, this is a pre-modeling step, right? This is a step that is meant to give us complete meter traces. We're talking about a small number of data points. If there are too many data points that are missing, then autocorrelation is not the answer. Some other form of disqualification, when Recurve makes a measurement on 10,000 meters or 100,000 meters or, whatever the size of the data set is, we're paying attention to things like how much data is missing. And we're not proposing using an interpolation method, any interpolation method, to fill in massive quantities of data that are missing. We're talking about using something like this in order to do a reasonable job of filling in missing data and then moving on with the main event, which is the formulation of the baseline model itself and the creation of the counterfactual into the reporting period. So I think we're maybe making a little bit much of this step. And again, we have metrics that will tell us whether or not we're making introducing some catastrophic issue in the baseline data itself. I do have a question. Armin, let's say that we're looking at a meter and we have a data point at 7 p.m. on a Wednesday that is missing. Let's say it's an observed data point. Now, is this method of interpolation taking other 7 p.m.s on maybe Thursday and Friday and Saturday and Sunday? Is it taking 8 p.m. and 9 p.m. and 10 p.m.? Is it sensitive to that in some way? How does this determination of which data points to actually pull in? I'd like a little more understanding of that.
Sure. Two things. One, thank you for mentioning that. Like, this is pre-modeling, so this is not in the modeling. We're just looking at the interpolation model to see if we are missing the data, can we successfully replace it in some sort of way or not. Two, as you mentioned, so if we are missing one single data point on 7 p.m. Wednesday, depend on the signal by itself. Let's say the model by itself decides, let's take a look at 10 lags and leads, and that 10 can be an hour before, an hour after, 10 hours before, 10 hour after, or any type of lead and lag that was on the highest rank of the autocorrelation, then that looks around that. Let's say those autocorrelation is 1 hour, 2 hours, 24 hours, and 48 hours. So basically, in that case, for that specific point, we look at 6 a.m., 6 p.m., 5 p.m., 8 p.m., 9 p.m., those values, and the values of 24 hours before, 24 hours after, and then take the mean value and replace that.
Got it. So it can be some combination of skipping over, entire days, taking 24, 48 hours and so forth, or it can be the hours right next, depending on the metric that you're determining from the rest of the data that is present.
Yes.
Can I ask a related question? So does it, when it's filling a gap, does it take into consideration what the values were on either side of the gap? So if it's, to take a toy example, it's picking data from 7 days before. It was very mild 7 days before. This is a hot day. So even though typically during the missing hour, energy use goes up 10% relative to the 2 hours surrounding it, the data from 7 days before was significantly lower.
Yeah.
Is it mirroring the shape and trying to meld the shape to the day that it's adding to, or is it just literally taking the mean value from the matching days?
Yeah. So as far as I could see for example, let's say focus on temperature. Temperature looks at 6. The optimal value for temperature was 6, and mostly it looks around that time frame that we have. For example, 7 p.m. it looks like 3 before and 3 after most of the times, and take the average for that. So most of the times you get the load shape of that. I mean, not the load shape, sorry, the curve shape of the temperature as the real data. So Travis 100% will talk about it. We test this on a huge data set with randomly removing days of data and random timestamps of the hours of data throughout the whole year for multiple IDs and population level. And with a different fraction of missing data, from very low fraction of missing data all the way to 50% missing data. And we check the accuracy for each of them. For temperature, we saw the most correlation is around 6. And for observed values is a little bit different, which Travis can talk about it. But basically, we're looking at that curvature rather than just randomly taking the mean values.
I mean, let me make sure that I understand this, and maybe this can help answer Ethan's question as well, about what hours we're using. You are basically saying you're missing data at 6 p.m. on Tuesday, say. To determine which hours to use to interpolate, you're looking at other 6 p.m. on Tuesday where you do have data and asking which hours before or after 6 p.m. on Tuesday have tended to be the most predictive or the most correlated with that temperature. And so it might be 7 p.m. and 5 p.m. on Tuesday, and it might be 6 p.m. on Monday and 6 p.m. on Wednesday are the ones that are giving you the most information. Or it might be like 6 p.m. on Monday and 6 p.m. on Thursday, or some other combination of things, but you're taking the ones that have the most predictive value for that particular case and using those to do the interpolation. So you're sort of inferring from the data itself which hours you should be using to interpolate, rather than having some fixed version of that. Is that correct?
Exactly.
Okay.
Yeah.
Yes.
But my understanding from what you guys explained before
Oh.
is each data set gets a unique set of lead and lag terms, but that not every point in each data set gets a unique set of lead and lag terms. So
Exactly.
look at the 8760 minus whatever gaps there are and say, this data seems to be on a, some weird pattern, and so they alternate days. This other one is on a very consistent 7-day pattern. This one is exactly the same every single day, and so we're just going to look at 3 hours before and after. Once that's established, the whole year uses the same pattern to fill gaps for that one data set.
Exactly.
Okay.
Exactly.
All right, and just going back to and I don't want to belabor this because you guys probably have some pretty graphs to help convince us that this is a good idea. The reason why we're not just doing what we did before, which is throwing out the data that had gaps that were too large to fill with linear interpolation, is because this model gets very, very grumpy if you throw out data for some reason. Is that true?
Yes. We have to have 24 hours complete in order to train the model on that. And if you have one single hour missing, the model will not work. we do have the option of throwing out the entire day, but then you're throwing out 23 good hours because you're missing one good. You've got one bad hour. It doesn't make sense.
Do you have a proposed threshold here? If there's only 1 hour left and there's 23 missing hours that you'd throw out the day or something?
We were going to leave the disqualification as the same as what it is with Caltrack. Caltrack is already pretty conservative. Now, that's not to say that we should not address this in the future. I think that we need to probably readdress all of the disqualification criteria in a future working group, daily, billing, hourly. But I think that that's kind of its own separate thing.
And the Caltrack, I'm sorry, I'm forgetting now. It's missing an hour or two a day is too much. Is the most you can fill?
With Caltrack hourly, it's you need 90% of all hours for every month.
Okay.
Yeah, so it's pretty stringent, you know.
Yep.
And I think do you guys have some, I think what
Population
you're
result?
going to show next is, you know, results of applying this interpolation procedure.
Yeah, let's.
Before going to the result, I would like to add one example here, and this is based on your comments, Adam. So we are anticipating with this autocorrelation interpolations, we are getting pretty good metrics. I would like to provide this example there. So consider, for example, a regression, and that regression is based on 10 data points. Between the data point, we have something, we can call it as a NAN. We are using the same regression to predict those values. Then in another regression, we are using those numbers predicted from the previous regression to develop the new regression. And this new regression should show pretty good result compared to the previous one. And the reason for that is we are using the same predictions to plug in the new values and consider those values as completely independent. So what I'm saying that mathematically, those metrics are not a good indications because we are not completely independently analyzing the values.
I disagree because what we're doing here is not that. This is not some cyclic approach to modeling that eats its own head. This is using test and train data. The test data is not being is not undergoing this procedure, and it's certainly not undergoing this procedure as informed by the baseline period.
I'd also like to just back out for a moment.
Okay.
What is the option? Like really, what other option do we have? We have missing data. The model does not work with missing data. What do we do?
Well, the other option is you throw out the day. If you
Yeah,
have
so
too
you
many
throw
days.
out 23 good hours because you have one missing hour.
Well, if you think, I mean, I'm just for the record, I'm willing to see how this stuff plays out because I'm very interested to see how your model's built on no missing data compared to artificially degraded data and how it fills in. I'm interested to see like the sort of proof and pudding there. But I think where I'm sympathetic to what most of us bringing up is that if your data, if your gap filling is giving you a low error coefficient, but actually the wrong answer, then you should have thrown it out and tried to build the model on the data that you're confident with. So that's I mean, I feel like that's the null hypothesis that we need to beat is, all right, so throw out the days, see how well the model does on building a regression with, I mean, I hear you, Travis, it hurts to throw out good data, but I think that's the alternative that we've got.
Yeah, I think that's totally fair. I just want to be abundantly clear here that we're not talking about the reason that we have a baseline model. The most important reason by far is to produce a counterfactual that is predictive. And we have gone through a very extensive and fairly sophisticated, and we've put just a lot of effort into developing a cross-validation approach to all of this that allows us to do these kinds of things and then understand how predictive the model is or is not. And what we are not doing is creating a baseline model and in any way making judgments that are informing the model formulation or the formulation of interpolation based only on, or really in any way, on the baseline model itself compared to the observed data. So we do not have this unholy cycle of filling in data and then fooling ourselves and then thinking that the model is better than it actually is because we're only comparing to baseline data. We've gone to great lengths to avoid exactly that in any fashion. So why don't we move on? And then if we want to come back to the topic of interpolation, we absolutely can. There's plenty more to talk about, believe it or not.
Well, we've got more plots to show that we're not crazy. This is actually prior to the model. We were removing data, so we know exactly what the data should be, and we can then directly compare to how good our interpolation is doing. So we said N. Armin and I have already said that for temperature, N is 6, and that for observed, N is unique. But how do we know that? How do we find what N is? So we have 8,253 meters from a combination of residential commercial, solar and non-solar. What we do is from these 8,253 meters, we randomly pick a day, we randomly pick an hour, and we randomly pick the amount of time missing. I believe the amount of time missing is pulled from a exponential or log normal distribution. I can't remember. It doesn't really matter. Point being, low number of hours is more likely because, well, if you have missing data, it's more likely to be an hour or two as opposed to days. But days does happen, so we want to also incorporate that as well. Then, since we have done this randomly, we repeat this 5 times just to make sure that we are not getting some crazy result for one single meter. This results in us doing this over 40,000 times. I'd call this pretty extensive. What we do here is we calculate the PNRMSE, and here we truly are calculating the error because we know what the values are that we are removing and that we are then interpolating over. So then we can actually calculate what the error is of our interpolation. We take the root mean squared area of that, and since these values are so different, we are again using the percentile normalized version of RMSE. And then in addition to that, with the plots that I'm going to be showing, I also normalized for each percent missing, because I should have mentioned when we're removing the data, we do this up to a specific percent that we are looking for. And the reason why I normalized for each percent missing is just so that it would look nice on the graph. It gives the same information. So to begin with, let's look at the temperature median. So here on the y-axis, this is the number of correlated indices. And on the x-axis is the missing fraction. This goes from 0.01 all the way up to 0.5. You will notice that we have a lot more data points here below 0.1. This is because the Caltrack and now OpenEEmeter disqualification criteria says that you cannot have any more than 10% of missing data. So most of our interest is below that. In addition, we have a lot more data points between 4 and 20. The reason why is through us just playing with this, we had an intuition that most likely our missing the number of correlated indices that we were going to want was going to be somewhere between 4 and 20. Now the dotted points, you'll notice that we see bright red points here. These points are the actual best for each percent missing. Oh, I should also mention the color here. For the color, What we really want is purple, because purple means that we have the lowest RMSE, the lowest error. We want to avoid the bright areas where this is where we have the most error. So coming back to these plots, the circles are the absolute best. They are the minimum for that given column. So this is 0.4, this is the best. And then we have two fits here. One is a dashed line, which is the global optimum, and one is a solid line, which is the panel optimum. Now let's look at some panels. So here, for the residential solar, you can see that you've got this bright flash at the top left, and if you have the very low values, so we're looking at like 4, it's 4 of our correlated indices. So we're seeing that by and large, we have just a straight line across. It doesn't matter what your missing fraction percent is. 6 is always the number that you want for correlated indices in order to have your best PNRMSE numbers in the population level, which includes over 40,000 different samples. We can look at the same thing for residential solar. You've got these points that are occasionally up above, but this is by and large noise. Mostly it's flat at 6. Same thing for commercial solar and non-solar. And I think that we've got some problems here with our titles, as these all say solar. But rest assured, these are actually non-solar and solar. So this is the easy result with temperature. Now, it gets a little bit more complicated with the observed. So with the observed, we have a bit of structure in the missing fraction percent versus the number of correlated indices. So this, again, remember that the solid line is the optimum fit for that panel. And this is driving me crazy. Armin, do you mind going and looking at some of the old plots and telling me if the left side or the right side is the non-solar? I know I
Check it right now.
got it somewhere. Excellent. Okay, so for this top left graph, this one is slightly different than all of the rest. For this one, we don't have much of a high spot on the top left, which means that we're pretty much safe no matter where we put this line, anywhere from, I don't know, 6, like it could come all the way down here, or it could come up high, and we would still be in a good place just based on the PNRMSE. Now for the top right, you can see that we clearly want to avoid this entire section here. So we really have a zone that we want to lie within, which is where the data points, the best data points and the best data fit exist, which these 3 panels are all kind of similar to each other. They're all much lower than this top left one. And we're seeing that overall, there's some noise here, but we're doing a pretty good job all across the board. But thank you. Non-solar is on the left, right's solar. Okay, so all of these on the left are non-solar. What we want to avoid, if at all possible, is to not have to add additional meta information in order to be able to do this interpolation. So it would be better for us if we had a global optimum like we did with temperature, but for the observed. So we did that. Oh, and the reason why we want to avoid having to use metadata is because what you classify as commercial or industrial can sometimes be questionable, and sometimes you've got people that have daycares out of their homes or other kind of pseudo-commercial buildings that are not listed as commercial. So it's better to have a global optimum that just works with everything. And for that, we end up with this dotted line. Now for the top left, that's the one that's really different from all of the rest, so it's not strange that the global optimum is a bit lower. We're still in the purple, so we're still going to get good results. Overall, I would say that I'm pretty happy with what I'm seeing here, particularly with the other 3, as this one almost looks exactly the same. This one, I would argue, is within error, and this one is also likely within error. So overall, by the way, this is the formula. Don't just try to make a Google thing go away on my screen. This is the formula that oh, did I mention that the x-axis on these were log scale? Because I meant to. And that's purely because of how the data turned out. Can I zoom in?
Yeah, I wanted to say, can you zoom in on that?
Yeah.
Or just make the image bigger on the slide or something, because yeah, it's really hard to see.
Yeah. All right, I'll just make this no bigger. All right. There we go. It's not quite as nice, but you can see the image better. Yes, so overall, this is log scale because that's the general structure of what we were seeing. And this is about 4 times the log of the percent missing plus this 24 number, which gives us all of these dashed lines. So it looks like we are doing pretty good in terms of error. And this is, again, not the error is not based on our model. The error is purely from the observed data, which we have masked and then interpolated over. So we know exactly what the answer should be. And again, we repeated this for 5 times for 8,000 meters, so that we've got a pretty good distribution of when the data point is missing, how much it's missing, what hour it starts on. All of that is random.
One thing I really wanted to add here, Travis, I just wanted to make sure. So if we have random missing data points, the result, the error is very small. I even looked at the raw load shape based on what we have as observed. Let's say we have all the observed for 8760, and then we intentionally remove data 10% randomly in different time slots, and the error is so close to 0 for most of the IDs that I as much as I could check individually one by one. And for this specific analysis, we select days, back-to-back days of missing data, remove them, and then we randomly remove the time slots, hours as well. So it's a really rigorous testing on the interpolation, and the error still is low. That shows 2 things. 1, the interpolation model is working, it's good enough. 2, the signals that we are working on, it's predictive by its own signal. So it has good cycle to it, both temperature and observed in most of the cases.
If you are going to, in OpenEEmeter, not allow more than 10% missing data still, and if with small amounts of missing data, you're getting really low error in all cases, would it not, for the sake of simplicity, be better to just pick 1 N, like 10 or something, if it doesn't matter that much?
So N actually changes from like 6 all the way up to probably 14 here, and this is all below 10%.
Right, but it also looks like it doesn't matter that much in that range, which N you pick.
True.
Yeah, they are fairly the same, so close. The
So it
percent differences.
Just the level of complexity seems like it might not be buying you that much additional value. Something to think about.
Ryan,
It's
I
hardly
hear
any
you
additional.
envisioning yourself explaining to non-technical stakeholders how the amount of interpolation is determined by a linear log-based like it's complicated enough as it is. But I mean, it looks like the line makes sense, but I hear you on the complexity. It's a lot to explain.
Mm.
I mean, is that the current recommendation? Is that we take this like log linear, probably a lookup table realistically, or whatever function you're going to use, and then you calculate the amount of missing data, use that to calculate the amount of neighbors that you allow the auto regression to pick, and then go from there?
Yes, except that would all be done under the hood inside
Oh,
of
sure.
the data class.
Yeah. No, I know the computers will do the hard work. Yeah, I mean, personally, I hear Brian's point. I vote for simplicity sounds nice. If you guys feel like it's giving a meaningful boost in accuracy, then I'll try to flip it around and say, this is so fancy, it has regressions on its regressions.
I remember trying to, at the start of this hourly working group, I went back and felt like we needed to give ourselves a understanding of how CalTrack 2.0 hourly worked. And, I ended up with like 15 slides. And I got myself to the point where I could explain CalTrack hourly. I was pretty proud. But I think for the most part, non-technical stakeholders don't need to understand this. What non-technical stakeholders need to understand is, generally speaking, how data is filled in, how, we don't have to be explaining autocorrelation and all that kind of stuff. Non-technical stakeholders don't need to understand, non-technical stakeholders, frankly, do not need to understand how intricacies of any of these models work. If we were bounding ourselves by the limits of non-technical stakeholder understanding, we would have very simplistic models that didn't work very well. So in that, I don't think that's the metric by which we should be judging ourselves.
That's basically where I'm at.
Is that fair to get that conclusion? And that conclusion is, if we miss 50% of the data points for the observed value, at the end of the day, with this procedure, let's call it a black box, we can get the same RMSE as the, for example, 1% missing value or less than 1%?
No. Travis, I wanted to send you some picture of raw data when we have 70% missing data. So, Mustafa, basically, if you have less missing data, like 10%, 1%, the accuracy is very, very good. You can, when you plot the load shapes, as you can see, if the missing points exactly follows the trend of the load shape. And these are basic, when you see dark circle, this is the population error of intentionally missing data and the observed by itself. So the more error, the more missing data point you have, the higher the error, but it's not so significantly higher.
But
The reason I have purposely normalized the PNR-MSE for every column of data. The reason for that is because the purpose of these plots was not to identify the exact PNR-MSE of what that result was to be. The purpose of these plots was to find out what is the lowest path through this surface. And so that was more easily found if I normalized the surface and everything has a base of 1. So whenever you see that over here on the right, it's 1, that's because it's been normalized to that percent missing.
Okay, so this is a nuance. How did you normalize the PNR-MSE?
I simply divided the column by the minimum.
By the minimum of the observed value?
By the minimum PNR-MSE of that column.
Okay, so if the minimum increase, probably you get the same kind of normalized value. And as Armin mentioned, that we have when we have a higher kind of missing fractions there, that minimum probably is going to be grow.
Yes, the actual error is going to be higher the further you go on to the right of this plot. The purpose wasn't to find what the error is or even to try to estimate that error. The purpose was to try to find what is the best number of correlated indices to use at that specific percent missing.
Okay, so in another language is if you have a like a regression and that regression have a very like a big error there, and when you are calculating that or comparing that one with the other regression which has a very good kind of predictions with the low error, by normalizing with the kind of based on the order of the magnitude for the errors, this is not apple by apple comparison because that those two regression end up with the same kind of normalized RMSE at the end of the day.
I think the request is we'd like to see the actual PNRMSE values for each of these data points, or especially for where we think this is going to be utilized. I think that's a very fair request.
Okay.
And we don't really need to look at it past 10%, right?
Nope.
And do you have any plots like the ones that Armin just described, showing some examples of this regression in action?
I just added one slide, slide 27, it's right after the appendix. Can you just look at it? That's 10% missing data for one random ID I just generated. And those, let me see if I need to save it. It's after appendix 27, slide 27. This is 10% missing data. And those red dots are actually the interpolated. And this is observed value.
So this is good. I'm glad we have this, but we also have population level results where we've done this. So I do think it is important, and it doesn't have to be like right now, but for the next working group, I think we need to present, what is the actual error in these data points, not just a normalized error. And that's fine.
Sure.
Yeah.
And this is the error that's just measured against the actual value that was artificially removed. So this is still no modeling whatsoever.
No, correct.
Yeah, so we'll work to get those plots. I think we do need to like calibrate this or ground it, in error metrics relative to those specific data points.
Sure. All right. So let's talk about we're going more in depth into our population level results, which we started this last session, but we said we had more to do there. So this is looking at solar, commercial / industrial. So here on the left, we have PNMBE, which is bias. For the bins here, on the y-axis is actually what I just said it was. The x-axis here are bins. And the bins have median temperatures, which you can refer to by this temperature on the secondary y-axis. Here on the right, we have the same thing except PNRMSE. So what we are doing here is we are binning by temperature, regardless of what season that is in, or what month, what day. We just want to know, do we have bias compared to our temperature? The reason why we're thinking that this one might be of interest is because the elastic net is a linear model, which means we are trying to fit something that we know is nonlinear, which is the observed meter data, with a linear function. Now, previously, we had hoped that because the way that the elastic net is actually creating a lot of different linear fits, that we might be bypassing this issue, but we just wanted to make sure that at at the final result, do we have temperature bias? All right. So now here on this left plot, I'd say this overall, this looks pretty good. So we're comparing the purple, which is our current model, versus Caltrack, which is the red here. The red is almost always upwards, so we're not balanced, roughly about 0. Whereas with the current model, we have smaller errors, and we do have some up and down, which is good. For the PNR-MSE, this one, remember when we were optimizing our function, we were optimizing it on PNR-MSE. So the current model is below Caltrack in almost every single case, except for the very last bin. The x-axis are the bins, and the bins, to identify what temperature they are, you can look at the red dots, and that's on the secondary y-axis. Could have done some better labeling, but this is what we have. An improvement with solar commercial industrial. However, we do have bias. And we start seeing this when we look at any of the other segments, and this is solar residential. So here, the current model has a clear structure to it, and this is almost certainly due to the linear function that we're fitting everything with, whereas the Caltrack is quite a bit lower everywhere. Now, despite that, the current model, because this is how we trained it, is still doing better than Caltrack in PNR-MSE in almost every single bin. Still, how do we reconcile this? Well, we reconcile this because imagine, for an instance, that you have slightly positive bias on your model. So all of your model, all of your data points are just a little bit below, and then imagine that you have, because with the PNR-MSE we're squaring everything, which means that we are putting more emphasis on larger values, which means that a whole bunch of low values can be canceled out by a single large value. This can easily result in having a lower PNR-MSE but higher PNMBE. Also, these things do cancel out with how mean bias error is calculated, so that you also have to take that into consideration. Well, all right. I mentioned this, it was like this for other segments, so let's look at some of those. Here we're looking at non-solar residential, which is also going to be a great place for us to start, because then we can directly compare to Caltrack on footing where Caltrack is meant to be used, which is non-solar. So again, we see that same kind of structure, except it's even more exaggerated in this instance. And again, the PNR-MSE is lower in every case on this plot. So at this point, I think I've made it clear that we have some kind of a bias problem in our current model. So the next question is, how do we fix that? This is basically what Caltrack 2.0 does. And what we can do is we can create n number of bins of temperature for each day. When I say each day, I am referring to the whole day. So like you take the mean of one day and you bin all of that. Same thing, we could do that with the median, the max, like some kind of aggregate function. And then what this would do is this would create unique linear models for these bins, which is exactly what Caltrack 2.0 does. The other idea that we have is we could linearize the temperature response. Now, what we would do here is we would alter the temperature within the model to linearize the response of the model. And we would likely do this with some kind of a kernel. This idea is not extremely well thought out. It's still kind of in its infancy. But one thing that we are certain of right now is that this would require multiple fits, because we would have to know if we are altering our temperature, like stretching it out or changing its distribution in some way, how does that affect the overall fit? And so this would all happen internally in the model, where we would basically have some transformation of the temperature from one plane to the next. and then that would always be the case within this model, and it would fit this within the baseline. Again, this is an idea on how we could fix this problem. Currently, we are attacking it by binning the temperature, which is our first choice because it is simpler and it also does not require multiple fits. Multiple fits means more computationally inefficient, which we would like to avoid. So, yep.
Can I just ask, how does the choice of linearizing temperature response compare to going to some kind of a degree days regressor?
Degree days would require that we have, so piecewise linear functions are a real pain to fit. I can tell you that from lots of experience with the daily model. I'd like to avoid it if at all possible. Particularly with an hourly model where you also have to take into consideration the time of day and stuff. We're basically getting back to Caltrack 2.0 at that point.
Well, Caltrack 2.0 hourly doesn't even have degree days, it has temperature bins. Yeah, Ethan, it's a good question. I mean, maybe you've thought about this more than I have. Whenever I've thought about degree days in an hourly model, so if you have hourly, I think it's pretty obvious we want hour of day to be something the model can consider because midnight is very different than 7 p.m. and
Sure.
we all get that. Do you then try to create degree hours for each hour? Potentially
Sure.
that's the thing to do, know?
Yeah. I mean, the reason
it's there's just more there than kind of meets the eye.
Yeah, no, it would be degree hours, but it's basically you're taking a min and max threshold on those. And the reason why degree days or degree hours or hourly basis degree days or all those different flavors show up in all these models is because thermostats drive load, and that's how thermostats work. So there's like a physical, it's not just like we came up with the most complicated possible way to fit the data. It's a very physical reality of what we know is driving it. I mean, the binning sort of got us around having to do multiple fits because we just let it find the inflection point, and one of the bins is a little wonky, but yeah, no worries.
Yeah. Well, I think the question we're sort of grappling with is the binning strategy sort of sufficient here? And if it is, then great. So, what Armin and Travis are going to show are just some preliminary results where, we haven't done anything in an optimized way, but we're starting to toy around with bins. And I don't want to step on their toes. It is looking fairly promising.
I mean, I will say that there's a couple of advantages. So the scary thing about bins is that you don't guarantee that your slopes are physically meaningful. But the nice thing about bins is that we get into these like nonlinear COP heat pumps. We get into potential for systems that max out and either like switch to a different fuel heating system or just like cap out on 100% capacity. And a bin model theoretically with enough data would actually deal with that properly, whereas the linear model just goes right off the end of the universe and starts to give you complete garbage at the ends.
Yeah.
So I mean, bins can be good. Sometimes it's a little scary, but I'm on board.
I can add one thing here. In the binning, we don't train different linear model in different bins. Basically, those bins are actually as a part of categorical data. So still we have that same speed of modeling within the one model, but basically it tweaks the parameters, the coefficients of the model in a way.
It's like an offset, kind of like the hour of week was in the old one.
Yeah.
Okay.
Exactly.
Well,
but we're changing it. We're trying to explore different ideas, different pathways we can do.
Okay.
So, continuing on here, We have explored this this first option somewhat. We have not explored the second option so much. And if the first one is successful enough, we likely will not look at linearizing the temperature response. Although it's entirely possible that the second choice here could be the better answer. It's also going to be the more computationally expensive answer, without a doubt. So, going back to that same non-solar residential that I was showing before, where Caltrack is on an equal basis, here this is what I was showing before, where we have that large change, and we have kept the y-axis the same here. You can see that by adding 5 temperature bins, where we are binning by the daily average, we were able to significantly decrease the bias. And keep in mind, this is not an optimized model by any means. We actually need to re-optimize the entire model for a combination of PNMBE and PNRMSE while adding in the number of bins as a new parameter that we have to optimize on top of, which is now the number of temperature bins, what the alpha is, which is the thing that downweights features, and as well as the percent lasso, which is what informs the elastic net on if it's doing an L1 penalty or an L2 penalty. So I'd say that binning currently looks like it could solve our problems. So we're pretty excited about this.
Do you have the result for the solar residential?
No, we do not. This is very preliminary.
Okay,
I mean,
so
it's the reason solar would be a little better, right, than before.
So my understanding is by having the temperature bins, you are introducing the independent variable, which is the temperature, to that autocorrelation. And I'm expecting to get a good result as you do. For the solar residential, if by adding the temperature bin, the result is not as good as the improvement for the non-solar one, probably you need to introduce the GHG bin as well, similar to the temperature, to get a better result there. And so on and so forth, like introducing multiple bins.
We were thinking about that too. I'm of 2 schools of thought on that. I think we should go through that exercise and see, because that may indeed be the case. But there's definitely, when you look at temperature in an unbinned, if you just look at observed data, like if you look at one of these style of plots and you just plot observed versus temperature, you get a U shape, because oftentimes you get increased consumption when it's cold, then you get decreased consumption when it gets more mild, and then it increases again when it gets hot. So you can see how having a linear model that kind of spans that entire range is just going to inherently struggle. But with solar irradiance, I would not expect that pattern to be the same. Like with solar irradiance, I'd be more concerned about things like saturating the solar PV system, when you get to a certain irradiance level. But I certainly wouldn't expect there to be any kind of like decrease and increase or like U shape. It's definitely going to be, you have the lowest solar irradiance, you have the lowest system output. You have the highest solar irradiance, you have the highest system output. So I'm not as concerned about that just inherently, but I think it's a good suggestion and it's worth trying for sure.
Can I suggest one more thing here? Instead of 5 temperature bin, increase the bins to, for example, instead of 5 to 7, 6, to see what is the change. Probably you may see a different, or maybe that U shape can be resolved.
Yeah, Mustafa, that's actually a really good idea. Both for the GHI and the changing the number of beans, we actually changed the number of beans from 5 to 20, and surprisingly, 5 was the ideal number, but this plot, it's based on 15 15 bins. So we are plotting based on 15 bins, but we are training based on 5 temperature bins.
So, but just to be clear, I think the number of bins needs to be needs to be subject to optimization. So, we need to let the computer tell us, should it be 3 bins, 4 bins, 5 bins, 6 bins, 8 bins, or whatever. And it needs to be, and that decision needs to be based on the testing data outputs, not the training data, because the more bins we introduce, the more we run the risk of overfitting as well.
8,760 bins.
Yeah, we just need 8,760 bins and we'll be good.
So I put this in the chat, but it'd be nice to see some. I don't know how to get you guys more cold weather data, or whether you think you've got a lead on that, because it's a little scary. I mean, on a lot of the residential, the hot temperature is the most likely peak behavior on electric, which is, for again, most of the country right now, the only place we're going to have hourly data is on the electric side, not gas. But as we get more heat pumps, I'm expecting to see more peaking on the cold weather side. And like, this chart scares the heck out of me, because at 40F, the PNMB starts to tank and you're like, what's next? What's next? How bad does it get?
I think what's happening there, Ethan, though, is, and this is not to say it's not a concern, but I don't think that sort of tanking is happening because we hit 40, and like anything below 40 is necessarily going to be worse. I think what's happening is it happens to be the lowest bin, and just like 93 or whatever it is happens to be the highest bin. So there may be some concern over the behavior of the lowest and the highest bins, and that's probably something that we should be paying close attention to. Maybe that's where there's the greatest degree of nonlinearity. I could absolutely see that being the case. But if a meter had weather data that went down to -20 and had a lot of it, then the binning itself, I think, would be modified in order to handle that. So I don't think what we're talking about here is defining temperature bins in the same way that Caltrac 2.0 defines them, where all meters get fit with a below 30 degrees and then 30 to 45 and then 45 to 60, or that's not what we're talking about. We're talking about more dynamic binning depending on the temperature range that's actually being experienced by any given meter.
Sure. And I mean, I think part of what I'm responding to is also just that if we had other data and it was like, okay, well, the extreme bins are always your outlier cases and they're less populated, and so yeah, it's still kind of a problem for the peak utility of OpenEEmeter, that it does a less good job at predicting your extreme peaks, and that's like a separate question. But if we had some meter data that had -20 outside conditions, and we're like, no, it's just the end bins, it's not that things go to hell after 40, you're like, okay, well, then that's a different problem. It's just a little hard for me to bring this back to cold parts of the country and be like, well, things look really great in between 35 and 80, so good to go, everyone. I don't know what happens.
Well, some of the meters in this sample definitely go well below 40. So potentially what we actually should do is, isolate the meters in the sample that do have temperatures that go well below 40, and just create a similar kind of analysis, but focused on those specific meters. Because what you're seeing here, this plot is binning temperature effectively across the entire population.
Right.
But again, like I said, like there's a subpopulation here that has temperatures that go well below that last bin.
Do you have any concerns that those cold weather buildings are predominantly vacation homes in the Sierras? Or I know that's
I don't know. I mean, you can always have that kind of thing, I suppose. Would love to have some more data, obviously to study. We're always working with what we got, as you know.
let me mention, yeah, no, I appreciate how much you guys are able to share and the quality of the data that you do have. But I'll mention this isn't entirely helpful because it's been mixed results, but we've been doing some studies with ResDoc hourly data. And the nice thing is that you have your disaggregated heating and cooling loads to, because that study is very concerned with the disaggregation value of the daily. And for a follow-up conversation, we're seeing some things with the new daily CalTrack that complicate the story a little bit. But it's nice to have a consistent data set from all across the country. However, the controls that seem to be in those fake buildings are rather aggressive. It seems like if you look at the actual hourly data, they'll come off a night of heating, and by 10 o'clock in the morning, they're like, now we're going to start cooling. I'm like, you were just heating an hour ago. Like, slow your roll. Where's your thermal mass? Where's your deadband? So we're seeing a little bit of like over exaggeration on the heating and cooling. But the nice thing is that you can very quickly get a full national data set. So, we've been sticking with it for that. There's also, oh no, it's not hourly. There's some free Florida data, but it's not hourly. So never mind that.
So I did consider using ResDoc or Comstock for this, and the reason why I chose not to is because at the end of the day, we are trying to model real meters,
Yeah.
and weird things happen in real meters that ResStock and Comstock just cannot capture. So
Totally.
if we're using those to train our model, I fear that we would be missing something.
Yeah, no, it's absolutely true. I mean, what we're doing is we're comparing a different model with the EEmeter first on the ResStock data, and then we'll try it on some actual data. And so it's sort of the trade-off of like, well, you kind of know the ground truth, although the ground truth isn't necessarily completely indicative. And then we'll try some real building data that has more realistic noise, but no ground truth whatsoever. And so, it's a couple points that we can hopefully triangulate in on.
Right.
So happy to show more about
I would say I've got two comments. I know we're running over time here, but it's a small group of us anyways. So for number one is your question about cold weather buildings. My expectation is this is not about cold weather or warm weather. This is about the range of temperature. So I would be more concerned about a building that sees -10 and 110 than I would be about a building that sees -50 and 0, for example. Because I think the concern here is the overall range, and is the number of bins, should that be a function of the temperature range that we see, or should that just be a static number? I don't know the answer to that.
Fixed width bins rather than a fixed number of bins.
That's what I'm leaning towards. It has its own complications that Armin and I have talked about, but that's what I would like to do. The other thing, oh, nope, lost the second. It's all right. We'll just move on. I'll do the ending real fast, and then we can catch back up on any other additional topics. So the next steps are that we would like to fix temperature bias. We're seeing positive results from binning, but is it sufficient, or do we need to do additional changes or go all the way to linearization? We need to update our objective function to include the PNMBE. The PNMBE is primarily going to be changed by the number of bins because the model itself is not going to be changed from how it works inside of sklearn. We would have to go in and modify the Python. It would be a headache. Third is that we need to reoptimize all of the hyperparameters because this is a similar but different model now. And then the last thing is the same thing that I had on this last meeting, which is we need to get the hourly model fully into OpenEEmeter, which includes the guardrails, the testing, the documentation, including the backlog documentation from the daily model. And that's that. Oh, nope. It was cold weather, and there was another thing that you had concern about that I was going to mention. I can't remember. It's fine.
Maybe you wanted to say
nonlinear
like
and
each meter ID has its own temperature bins rather than same
Yes.
temperature for everything.
Yes. And that also means that our model is not going to be tied to Fahrenheit. It could be used for anything. Maybe one day we'll move to the scientific Kelvin.
We got to go to Rankin if we're gonna do anything, man.
We're not doing engines. Rankin only belongs in engines.
Good discussion today. I think, obviously there's a little more under the hood here than we might have anticipated when we first created the optimization around the existing hyperparameters, but it's all for the better. And I think we're going to end up in a good place here, but potentially with some questions we still should work on together as a group, even after the first version of this model is released. So one of the things I would just remind everybody of is we want to get a good model out. We don't want to have catastrophic issues floating around in the model, but that doesn't necessarily mean that the model can't be improved over time as the group, if and when we need to as a group. So definitely appreciate all the feedback, Ethan. Thank you in particular for all the I think you more than anybody have really helped us hone our thinking here. So we really appreciate that.
Absolutely
well,
agree.
thanks for all the work you've put in. I really appreciate all the improvements that you're making, and I know this is hard stuff. It's easy to show up once a month and poke holes and be like, math harder, but I do appreciate it.
Yeah, guys, that's going to be the theme for the next month before the next working group is just math harder. I'm going to crack the whip. So I'm going to crack the whip with that as the theme. Well, yeah. Well, thank you, Travis, and thank you, Armin. It's a ton of work to put together this every month. So, I appreciate it too. I come to these working groups and I learn a lot.
Absolutely. All right.
We'll see you next time.
All right. See ya.